In computational complexity theory, the exponential time hypothesis is an unproven computational hardness assumption that was formulated by Impagliazzo and Paturi. The hypothesis states that 3SAT cannot be solved in subexponential time in the worst case. The exponential time hypothesis, if true, would imply that PNP, but it is a stronger statement. It can be used to show that many computational problems are equivalent in complexity, in the sense that if one of them has a subexponential time algorithm then they all do. Definition: K-SAT is the problem of testing whether a Boolean formula, in conjunctive normal form with at most k variables per clause, can be made to be true by some assignment of Boolean values to its variables. For each integer k2, define a real number sk to be the infimum of the real numbers delta for which there exists an algorithm solving K-SAT in time O, where n is the number of variables in the given K-SAT instance. Then S2 equals 0, because 2SAT can be solved in polynomial time. The exponential time hypothesis is the conjecture that, for every k greater than 2, sk greater than 0, clearly, S3 S4, so it is equivalent to assume that S3 greater than 0, the positivity of the remaining numbers sk follows automatically from this assumption. Some sources define the exponential time hypothesis to be the slightly weaker statement that 3SAT cannot be solved in time 2O. If there existed an algorithm to solve 3SAT in time 2O, then clearly S3 would equal 0. However, it is consistent with current knowledge that there could be a sequence of 3SAT algorithms, each with running time O for a sequence of numbers delta I tending towards 0. But where the descriptions of these algorithms are so quickly growing that a single algorithm could not automatically select and run the most appropriate one, because the numbers S3, S4, form a monotonic sequence that is bounded above by 1, they must converge to a limit S infinity. The strong exponential time hypothesis is the assumption that the limiting value S infinity of the sequence of numbers sk equals 1. Another variant is the non-uniform exponential time hypothesis, a strengthening of the second phrasing of the eth, which posits that there is no family of algorithms that can solve 3SAT in time 2O. Implications for satisfiability. It is not possible for sk to equal S infinity for any finite k. As Impagliazzo, Paturi and Zane showed, there exists a constant alpha such that sk S infinity. Therefore, if the exponential time hypothesis is true, there must be infinitely many values of k for which sk differs from sk plus 1. An important tool in this area is the Sparsification lemma of Impagliazzo, Paturi and Zane, which shows that, for any epsilon greater than 0, any KCNF formula can be replaced by O simpler KCNF formulas in which each variable appears only a constant number of times, and therefore in which the number of clauses is linear. The Sparsification lemma is proven by repeatedly finding large sets of clauses that have a non-empty common intersection in a given formula, and replacing the formula by two simpler formulas, one of which has each of these clauses replaced by their common intersection and the other of which has the intersection removed from each clause. By applying the Sparsification lemma and then using new variables to split the clauses, one may then obtain a set of O3CNF formulas, each with a linear number of variables, such that the original KCNF formula is satisfiable if and only if at least one of these three CNF formulas is satisfiable. Therefore, if 3SAT could be solved in subexponential time, one could use this reduction to solve K-SAT in subexponential time as well. Equivalently, if sk greater than 0 for any k greater than 3, then S3 greater than 0 as well, and the exponential time hypothesis would be true. The limiting value S infinity of the sequence of numbers sk is at most equal to SCNF. where SCNF is the infimum of the numbers delta such that satisfiability of conjunctive normal form formulas without clause length limits can be solved in time O. Therefore, if the strong exponential time hypothesis is true, then there would be no algorithm for general CNF satisfiability that is significantly faster than testing all possible truth assignments. However, if the strong exponential time hypothesis fails, it would still be possible for SCNF to equal 1. Implications for other search problems. The exponential time hypothesis implies that many other problems in the complexity class SNP do not have algorithms whose running time is faster than Cn for some constant C. These problems include graph K-colorability, finding Hamiltonian cycles, maximum cliques, maximum independent sets, and vertex cover on n-vertex graphs. Conversely, if any of these problems has a subexponential algorithm, then the exponential time hypothesis could be shown to be false. If cliques or independent sets of logarithmic size could be found in polynomial time, the exponential time hypothesis would be false. Therefore, even though finding cliques or independent sets of such small size is unlikely to be NP-complete, the exponential time hypothesis implies that these problems are non-polynomial. More generally, the exponential time hypothesis implies that it is not possible to find cliques or independent sets of size k in time No. The exponential time hypothesis also implies that it is not possible to solve the k-sum problem in time No. The strong exponential time hypothesis implies that it is not possible to find k-vertex dominating sets more quickly than in time nk-0. The exponential time hypothesis implies also that the weighted feedback arc set tournament problem does not have a parameterized algorithm with running time O**. It does have, though, a parameterized algorithm with running time O**. The strong exponential time hypothesis leads to tight bounds on the parameterized complexity of several graph problems on graphs of bounded tree width. In particular, if the strong exponential time hypothesis is true, then the optimal time bound for finding independent sets on graphs of tree width W is WNO. The optimal time for the dominating set problem is WNO. The optimum time for maximum cut is WNO, and the optimum time for K-coloring is WNO. Equivalently, any improvement on these running times would falsify the strong exponential time hypothesis. The exponential time hypothesis also implies that any fixed parameter tractable algorithm for edge clique cover must have double exponential dependence on the parameter. Implications in communication complexity. In the three-party set disjointness problem in communication complexity, three subsets of the integers in some range 1, m, are specified, and three communicating parties each know two of the three subsets. The goal is for the parties to transmit as few bits to each other on a shared communications channel in order for one of the parties to be able to determine whether the intersection of the three sets is empty or non-empty. A trivial m-bit communications protocol would be for one of the three parties to transmit a bit vector describing the intersection of the two sets known to that party, after which either of the two remaining parties can determine the emptiness of the intersection. However, if there exists a protocol that solves the problem with O communication and 2O computation, it could be transformed into an algorithm for solving k-sat in time O for any fixed constant k, violating the strong exponential time hypothesis. Therefore, the strong exponential time hypothesis implies either that the trivial protocol for three-party set disjointness is optimal, or that any better protocol requires an exponential amount of computation. Implications in structural complexity. If the exponential time hypothesis is true, then 3SAT would not have a polynomial time algorithm, and therefore it would follow that PNP. More strongly, in this case, 3SAT could not even have a quasi-polynomial time algorithm, so NP could not be a subset of QP. However, if the exponential time hypothesis fails, it would have no implication for the P versus NP problem. There exist NP-complete problems for which the best-known running times have the form O for C less than 1. And if the best possible running time for 3 SAT were of this form, then P would be unequal to NP, but the exponential time hypothesis would be false. In parameterized complexity theory, because the exponential time hypothesis implies that there does not exist a fixed parameter tractable algorithm for maximum clique, it also implies that W1 FPT. It is an important open problem in this area whether this implication can be reversed. Does W1 FPT imply the exponential time hypothesis? There is a hierarchy of parameterized complexity classes called the M hierarchy that interleaves the W hierarchy in the sense that, for all I, M, I, W, I, M, I plus 1, for instance, the problem of finding a vertex cover of size k log n in an n-vertex graph with parameter k is complete for M1. The exponential time hypothesis is equivalent to the statement that M1 FPT, and the question of whether Mi equals Wi for I greater than 1 is also open. It is also possible to prove implications in the other direction. From the failure of a variation of the strong exponential time hypothesis to separations of complexity classes. As Williams shows, if there exists an algorithm A that solves Boolean circuit satisfiability in time 2n f for some superpolynomially growing function f, then any exptime is not a subset of P-poly. Williams shows that, if algorithm A exists, and a family of circuits simulating an exptime in P-poly also existed, then algorithm A could be composed with the circuits to simulate an exptime problems non-deterministically in a smaller amount of time, violating the time hierarchy theorem. Therefore, the existence of algorithm A proves the non-existence of the family of circuits and the separation of these two complexity classes.